In the last class, we had seen operations with respect to vectors, and we looked at the dot product of vectors, we looked at the cross product of vectors, and we saw how we can carry out the vector operations. Today, we will come back to kinematics and we will look at motion in a plane. So, let us say a particle is moving along some path which I have drawn here, and in a plane, in a general way, this will be a curved path. So, let us say the particle is at a position P at time t. We are studying this with respect to some reference frame in which we have fixed coordinate axis. So, let the position vector of this particle at time t be given by vector r at time t. At a time t plus delta t later, that means at a time delta t later, the particle reaches the position p prime, which we denote as p prime as t plus delta t, and the position vector here is given as r at t plus delta t. Now, in this coordinate frame, which is x, y, z, since we are talking of a planar system, the z axis will always, the z coordinate will always be 0. So, we are looking at its coordinates in x, y. At this position P, let the x, y coordinates be x comma y, and at the position P prime, let the coordinates be x plus delta x and y plus delta y. And the vector P prime, this vector we will call it as this is the displacement vector, which we represent by delta r. So, now what we have seen is, if we write the vector P prime, this is equal to the vector delta r, and this is equal to r at t plus delta t minus r at t. And what we have seen is that the instantaneous velocity of a particle at the point P, this is defined as limit delta t going to 0, r at t plus delta t minus the vector r at t divided by delta t, or which we also know this is equal to the derivative of the vector r. So, this is the instantaneous velocity of the particle at P, and this is very much the same as in one dimensional motion, but now because this is two dimensional motion, we have the difference is between two vectors. And we can also realize this, that r at t plus delta t, this is equal to x plus delta x I plus y plus delta y j, and r at t is equal to x I plus y j. So, therefore, delta r can be written as delta x I plus delta y j. That means, we are taking the scalar components of the vector delta r, and therefore, the vector v then becomes equal to delta x by delta t I plus delta y by delta t j, and this we can also write it as Vxi plus Vyj, where Vx will be the x component of the velocity and Vy will be the y component of velocity. Now, here we have defined this for an instantaneous case. In case if delta t is a finite interval, that means it is not very small, then we talk of average velocities, and the average velocity in that case we will talk of it as v, and we will put an average sign, and this will be equal to delta r by delta t. And in this case, when we talk of average velocity, the limit delta t going to 0 will not be there. This can be defined for any delta t. Now, we also realize that the direction of the velocity is the same as direction of delta r, and which, if we go back to our picture here, delta r is in this direction. So, velocity will be in the direction of delta r, and in the limit delta t goes to 0, this direction will become tangent to the path. So, in the, let us write this down, that in the limit the direction of delta r is tangent to the path. So, that means the direction of the velocity is always tangent to the path. And this, if you think in physical terms, will also make sense, because something which is travelling along in a particular direction cannot pierce that direction. Something moving along a path has to be on that path, it cannot go inside or it cannot separate away from the path. So, direction of v is always tangent to the path. And if we look at the magnitude of v, so what we have also seen is this velocity v, we can write it as vxi plus vyj, if we write it in terms of x and y components, and the magnitude of v, if we write it like this will be equal to square root of vx square plus vy square, and sometimes we also write this as v, or we may write it like this, v without the vector sign. So, that is the symbol for the velocity v. And also what we see is, if this is vx, this is vy, and if this angle is theta, then the direction which the velocity vector makes tangent of theta, that is given by vy upon vx. So, the magnitude is square root of vx square plus vy square, the direction is given by tan theta is equal to vy by bx, or we write the two components vx and vy. So, these two things are equivalent. Next, we will like to consider in this topic will be the concept of relative velocity in two-dimensional motion. And this is exactly the same as relative velocity in one-dimensional motion, but now because the velocities have different directions. So, these now will have to be dealt with in a vector manner. That means, suppose if a particle A has a velocity Va and a particle B has velocity Vb, both of which are measured with respect to some frame of reference, then velocity of A with respect to B can be written as Va minus Vb, or sometimes this is also written as relative velocity of A with respect to B. So, the concept of relative velocity we have seen in 1D motion, it is the same here, but now we will have to take Va and Vb as vectors, and this will be a vector subtraction. So, for example, if raindrops are falling in this direction and a person is moving on a bicycle in this direction, then this will be equal to the velocity of the rain with respect to the bicycle, because V bicycle plus V rain with respect to bicycle, the sum of that will be equal to the velocity of the rain. So, therefore, if a person is moving on a bicycle in this direction and the rain is moving vertically down on him, the person will feel the raindrops to be coming in at an angle given by the vector which is given by the subtraction of these two vectors. Next, we move on to acceleration of a particle, which we denote by vector A. And as we have seen, acceleration is given as the rate of change of velocity. So, if the velocity at time t is v t and velocity at time t plus delta t is v at t plus delta t, then we can write delta v as equal to v at t plus delta t minus the vector v at t, and acceleration will be given by limit delta t going to 0, v at t plus delta t minus v at t divided by delta t. So, we look at the velocity vectors at the 2 points, take the difference of these two, and that gives us the acceleration. And in case if delta t is not very small, if it is a finite interval, then the acceleration we get is the average acceleration. So, and as before, we can also write the acceleration as axi plus ayj, where ax is the x component of acceleration, and this is equal to delta Vx by delta t, and Ay is the y component of acceleration, given by the change in Vy by delta t. So, therefore, we have this quantity acceleration, and what we can see here is that the x component of acceleration, which is the derivative of the x component of velocity, is nothing but d by dt of dx by dt, and this can also be written as the second derivative of x with respect to time, and similarly the y component of acceleration is dvy by dt, and this can be written as d by dt of dy by dt, and this will be the second derivative of the y component of displacement will be given by this. Now, let us try to see some subtle points about acceleration. When a particle moves in a straight line, then clearly velocity and acceleration are along the same direction, which is given as, which will be given by the direction of the line. Of course, it can have a negative sign, which means it could be in against that direction, but in general that vector direction will be the same, it will be along that. But when a particle is moving in a curved path, then first thing we have seen is the direction of velocity at any instant is tangent to the path. Now, what about the acceleration? Is the acceleration tangent to the path, or does it have some other component? And to understand this, let us go back to this picture. Let us say the particle, this is the position p, this is the position p prime. Now, when we look at this, this is the direction of v at this instant is tangent to the path here, and the direction of p prime, velocity at p prime will be tangent to the path at p prime. So, now here if we look at acceleration, so let's plot the two velocity vectors with their tails together. So, we have the vector v here and we have the vector v prime here, and this vector which connects these two, this is the vector delta v. And now we know that acceleration is equal to delta v by delta t. So, the direction of acceleration has to be along delta v, and which clearly is not along the tangent. And so, what we see is that on a curved path there are acceleration on a curved path is due to two components. The first component comes because of a change in speed of the particle, and this is the component which also comes when a particle is moving along a straight line. So, there is a change in speed of the particle, and this component is always, because even if the particle is moving along the same direction, if its speed changes, there is an acceleration. So, this component is along the direction where the velocity is, that is, it is along E t. But in addition to this, we have a second component of acceleration which is perpendicular to this direction, and this comes because the direction of velocity changes due to the curved nature of the path. So, here even if the magnitudes of v and v prime are equal, but because their directions are different, so that will lead to a component of delta v which is basically perpendicular to the E t direction, and this component is actually the second component or the perpendicular component which is perpendicular to E t. If the particle is moving in a curved path, this component points towards the, so if we are at this location, if we assume this is a circular type of motion, it points toward the center of the circle in which the particle is moving. Now, the actual shape may not be a circle, but we can locally assume that it is a circular path, then this is pointing toward the center of that circular path, and if this is the tangential direction, this direction is perpendicular to the tangent. Sometimes it is called the normal direction. So, we will call it as E n. So, we have these two vectors E t and E n, and the normal component of acceleration we can show. This is, first of all, it is proportional to the square of the speed. So, whatever is the speed of the particle at this point, this will be proportional to the speed square, and if locally the particle is moving in a circle of radius r. So, that means if we at this instant we assume it is a local circle, and if the radius of that circle is r, then acceleration, the normal component of acceleration, this is given by v square upon r, and r is called the radius of curvature of the path. So, this is something which we should always keep in mind, that when a particle moves on a curved path, there will be two components. If it one component which is due to the rate of change of speed of the particle, or and the other component even if the particle is moving at a constant speed, because of the curved nature of the path, there is a component of acceleration which is perpendicular to the path. So, now having seen these things, what we can do is we can have a look at motion of a particle in uniform circular motion. So, we look at a particle which is following a circular path, and the word uniform implies that it is moving with a constant speed. So, if we plot this here, if this is a circle, if we have a particle which is moving along this circle or the circumference of the circle with a constant speed, then we say it is in uniform circular motion. So, here now let us say the particle is moving with a constant speed which is given by v. If the particle is at this position p, then from what we have seen, if let us first say the radius of this circle is r, then if we look at the acceleration at point p, the speed of the particle is constant, but this does not mean that the acceleration is 0. The acceleration at point p will point toward the center of the circle, and this will be given by v square by r in a direction toward the center of the circle. So, this arrow here represents the direction of the acceleration. Its magnitude is the speed square divided by r. Now, there is some terminology which we define with uniform circular motion. So, the first thing which we see is, even though the speed is constant in a uniform circular motion, the acceleration is not 0. Now, let us say the particle travels from p to p prime, and the angle with the center of the circle is given by delta theta. So, if delta theta is the angle which is covered by the particle with respect to the center of the circle. So, now this delta theta is also referred to as the angular displacement, and if delta t is the time taken for particle to go from p to p prime, then we define a quantity called angular velocity. The angular velocity of the particle is defined as the angle delta theta by delta t, and the symbol often used for angular velocity is the Greek letter omega. So, the angular velocity, as we have seen, this is given by delta theta by delta t. Now, if we try to find the speed of the particle, the speed will be given by the distance p p prime divided by delta t. So, if we look at this, so speed of the particle is equal to the distance covered by the particle divided by delta t, which is the arc p p prime divided by delta t, and this will be nothing but r delta theta upon delta t. So, we can see that the speed is given by r times omega. And if we look at the acceleration of the particle, this is given by v square upon r. So, this is equal to r square omega square upon r, and this is equal to r omega square. Now, this component of the acceleration which is toward the center, we have a name for this. This is also called the centripetal acceleration. It is always, as we have seen, pointing toward the center of the particle. Now, there are a couple of other terminologies which we define. One is the time taken for one revolution. This is called the time period, and the symbol used for this is capital T. the number of revolutions made in 1 second. This is defined as the frequency, and this will be equal to 1 over t, and the symbol used for frequency is the Greek letter nu. Now, if we look at omega, omega is nothing but the angular displacement divided by time, and if we want to express omega in terms of the time period t, then the angular displacement for one revolution, the angle is 2 pi radians and the time is t. So, therefore, omega will be equal to 2 pi upon t, and this, so we have omega is equal to 2 pi upon t, which we can also write it as 2 pi nu, because nu is equal to 1 over t. And if we look at now the velocity in terms of omega, velocity is equal to r omega. So, this can be written as 2 pi r nu, and acceleration, which is equal to r omega square, will be equal to 4 pi square nu square r. So, in terms of frequency and time period, we can get the values of velocity and acceleration. Now, this will be valid, the time period will be constant if we have uniform circular motion. Let's just briefly see what happens if circular motion is not uniform. That means the speed of the particle changes. So, now if speed of the particle changes, this will also imply that omega will not be constant, and we can define a quantity called the angular acceleration, which is equal to the rate of change of omega with time. And at this point, what I will specify here is, I will not prove this, but we will show that even for general circular motion, velocity is given by r omega along the et direction. So, this would be the instantaneous velocity, as omega is not constant, and the acceleration will be given by r times d omega by dt along the et direction, and we will have plus r omega square along en direction. And this we can also write it as r times alpha along et plus r omega square en. So, therefore, when a particle is moving in a circular path, there are two components to its acceleration. A component of the acceleration which is toward the center, which stays the same as it was in uniform circular motion, equal to r omega square, and there is a tangential component of acceleration which is equal to r times alpha, and the velocity still continues to be r omega irrespective of the value of alpha. So, we have seen circular motion. Let us now take the case of a particle which is moving with constant acceleration. That means the acceleration is equal to constant both in magnitude as well as direction. And let us say that a particle which is undergoing constant acceleration, let its velocity be v0 at time t is equal to 0, and let it be velocity v at time t. So, what we would like to find out is what will be the velocity v of this particle at time t, and if the particle is at a position r0 at t is equal to 0, then what will be its position at a time t later if it is moving with constant acceleration. So, the first thing we do is, we know the acceleration is constant. So, if we write this acceleration as v minus v 0 divided by the time t, which is t minus 0. So, this is equal to v minus v 0 upon t, and what we get is the velocity v will be equal to v 0 plus a times t. And if we write it in the component form, we get our usual equations. Vx is equal to v 0 x plus ax times t, and Vy is equal to v 0 y plus ay t, where the acceleration a is equal to axi plus ayj, the velocity v is equal to vxi plus vyj, and the initial velocity v 0 is equal to v 0 xi plus v 0 yj. So, this is the first expression which we get, and now we work out the position vector. So, we want to find the position vector r at time t, given that position vector is r 0 at t is equal to 0. So, now to do this, we see that the average velocity between time t and time 0, this will be given by v 0 plus v divided by 2, and so the displacement, which is equal to r minus r 0, this will be given by the average velocity times t. This works out because the acceleration is constant. So, therefore, this we can write it as equal to v 0 plus v 0 plus at by 2 times t. So, putting all this, what we will get is r minus r 0 is equal to v 0 t plus half a times t square, and this gives us r is equal to r 0 plus v 0 t plus half a t square. And again we can write this along x and y directions separately. So, we will get this as x is equal to x 0 plus v 0 x t plus half a x t square, and we write the y component, that will give us y is equal to y 0 plus v 0 y t plus half a y t square. Now, notice both of these equations are as if the particle is moving along x direction and y direction in an independent way, and we can treat the motions separately with accelerations a x and a y in an independent way. But if we want to find the equation of the path of the particle, then what we will have to do is we have to relate x to y. That will give us the path of the particle, and for that what we will have to do is we will have to eliminate time between these two equations, and that will give us x as a function of y or y as a function of x. Now, we look at a special case of motion under uniform acceleration or constant acceleration, and which is called projectile motion. So, projectile motion is the motion of a particle which is travelling under the influence of gravity. So, this is a special case of motion which we have seen of constant acceleration motion, assuming that the acceleration due to gravity does not change in the range of motion which we are considering. So, here what we examples of motion like this would be the path or motion of a cricket ball after it has been hit by the bat or after it has been delivered from the hand of a bowler, motion of a bullet after it leaves the gun. All these motions would be cases of projectile motion. Now, if you try to think of what the difference between this projectile motion and a body which has been thrown just vertically up. Let us say I have a ball in my hand, or I take this pen, I throw it up vertically. Now, this is a special case of projectile motion, but when I talk of projectile motion, it could also be a case where when I throw the body, it also has a horizontal component of velocity. So, what we consider under projectile motion is not just a body which is moving vertically, but it could also move horizontally, because initially the body has an x component of velocity. So, let us try to work this out. What we have is, so projectile can have an x component of velocity at time t is equal to 0. And then we will see, because it has some component of velocity at t is equal to 0, and because let us define we define the upward direction as plus y, and x is the horizontal direction. So, therefore, first let us write the acceleration vector. The acceleration vector will be equal to 0 I minus g j. That means, there is no acceleration in the x direction. In the y direction, the acceleration is equal to minus g, and we take t is equal to 0 is the initial time, and let the particle be at 0 0, that means at the origin at time t is equal to 0, and its initial velocity is given by v 0, which we can say that means, so that means we are saying this is the origin, the particle is at this location and it has velocity v 0, which we can also express it as the speed v 0 and the angle theta 0 with the horizontal which the velocity, initial velocity makes. So, here we can see that the x component of the initial velocity will be given by v 0 cos theta 0, and the y component of the initial velocity will be given by v 0 sin theta 0. So, if we know the initial component of the velocity, initial velocity vector, that means both the components of the velocities are known to us, and then what we want to determine is we wish to find the coordinates of the projectile or of the particle p at a later time. Now, let us briefly, before we look at the equations, let us physically look at the projectile motion before we come to the equations. So, the particle has been released at time t is equal to 0, its x component of velocity is v 0 cos theta 0, its y component of velocity is v 0 sin theta 0, and the acceleration which it is experiencing is only in the minus y direction. The acceleration in the x direction is 0. That means, throughout its motion the x velocity will not change, that will be equal to v 0 cos theta 0. If we look at the y component of velocity, initially it is v 0 sin theta 0, there is a negative acceleration minus g. So, therefore, this component will reduce and it will go to 0, and after which we see the particle experiences throughout it has been experiencing an acceleration of minus g. So, once the velocity in the vertical direction reaches 0, the particle will start moving downwards, which is in the direction of minus y, and it will, the speed of the particle will keep on increasing because it has started from 0 speed and it will then eventually touch the ground. Now, there is a term which we define: if the particle has started from the origin, the point at which it falls back on the surface, which means where y becomes 0 again, this distance from the origin is called the range, and we will work out what is how do we work out range in terms of these given parameters. So, let us now analyze the motion of a projectile. So, as we have seen, its acceleration is equal to minus g j, that means a x is equal to 0, a y is equal to minus g, its initial velocity v 0, this is equal to v 0 cos theta 0 I plus v 0 sin theta 0 j, and the initial point is the origin, which is 0 0, which means x 0 is 0 and y 0 is also equal to 0. So, now if we look at the x component, x is equal to, because the velocity in the x direction is constant. So, at any later time x component is given by v 0 t. So, this will be equal to v 0 cos theta 0 times t. So, that gives us the value of the x coordinate of the projectile. The y coordinate will be given by v 0 sin theta 0 t minus half g t square. The minus sign comes because acceleration is minus g. So, we have, and also if we write the velocity v x at any later time, this is equal to v 0 cos theta 0 and v y is equal to v 0 sin theta 0 minus g t. These are like the one dimensional equations of motion for x and y written separately. And from this we also realize that the y direction of the motion of the particle is exactly the same as the y direction of motion of a particle which is thrown vertically upwards with a initial speed of v 0 sin theta 0, that is the initial vertical speed of this particle. That what I am trying to, what we understand from this is that if a particle is thrown vertically up with some speed, and if it is thrown as a projectile at an angle theta 0 such that the two vertical speeds are the same, then both the particles will come back to the ground at the same time. So, here now if we want to find the path of the projectile, we will use these two equations and we will eliminate the value of t. We will eliminate time to get y as a function of x. So, when we continue this, it is the easiest way to do this will be to go to this x equation. So, we have x, t is equal to x divided by v 0 cos theta 0, and we put this value of t in the y equation. So, we will get y is equal to v 0 sin theta 0 into t, which is x by v 0 cos theta 0 minus half g into t square. So, x square upon v 0 square cos square theta 0. So, this gives us, when we simplify this, this is equal to tangent of theta 0 times x minus half g divided by v 0 square cos square theta 0 times x square, and this is of the form equal to ax plus bx square, where a is equal to tangent of theta 0 and b is equal to minus half g by v0 square cos square theta 0, and this is the equation of a parabola. That means a particle which is thrown as a projectile has the path taken by that is that of a parabola. Now, let us calculate some of the quantities. First, if we want to find the time taken for the projectile to reach maximum height. To find this time, what we will have to do is we put Vy is equal to 0 and we have Vy is equal to Vy 0 minus Gt. So, that will give us T is equal to Vy 0 upon G. So, that will be equal to V0 sin theta 0 upon G. So, this is the time taken for the projectile to reach maximum height. Well, you will probably also be able to realize that twice of this will be the time taken for the particle to fall back on the ground. And if we work out the, so this is the time taken, and the maximum height will be given by y at this time t. So, this will be equal to V0 sin theta 0 times we put in the value of t. So, that is equal to V0 sin theta 0 by g minus half g times t square. So, t square is V0 square sin theta 0 square upon g square, and so the maximum height which the projectile attains comes out to be equal to V0 square sin square theta 0 upon 2g. Now, to find out the range, first we work out the time taken for the flight. That means we first find out the time taken. Now, this is the time at which y is equal to 0. So, therefore, we put this in the equation. So, the time at which y is equal to 0, so we will get 0 is equal to V0 sin theta 0 t minus half gt square. So, we will get this this time, which is the time for the flight, this will be equal to 2 V0 sin theta 0 upon g, and this we had already said when we worked out the time taken for the maximum height. This is twice of that, and the range will be the x coordinate for this, which will be equal to V0 cos theta 0 times Tf. So, this will be equal to V0 cos theta 0 times 2 V0 sin theta 0 upon g, and this becomes equal to V0 square sin of 2 theta 0 upon g. So, we have seen the formula for the range. Now, there should be one I would like to emphasize that the formulas which we have derived, we are assuming when we talk of range that we have started from the origin and we want to find the position when the particle comes back to the same level, and for that we have worked out a formula for the range. But we could have different initial conditions. For example, you could have a case where a particle is being thrown from a certain height, and then you want to find the x distance at which it strikes the ground. Now, the formula for range derived here is not going to work here, because here the particle is starting from some location x0 y0 which is not equal to 0. So, when we have situations like this, we have to go back to our original equations. We have to see that the acceleration in the x direction is 0, acceleration in the y direction is minus g, and we work out with x not x0 and y0 not being 0 0, but being the values what you start with, and then you can work out the different x and y coordinates as a function of time. So, these things should be taken into account. Now, when we look at the formula for range as we have done in this case, then what we see is the formula for range gives us so for a given velocity, when we want to have a maximum range, then that will happen when theta 0 or sin 2 theta 0 has to be 1, which means that the maximum range for a given V 0 occurs at theta 0 is equal to 45 degrees. So, if you want something to go at a farthest distance, the angle with which it should be aimed should be the velocity should have a 45 degrees with the horizontal. In projectile motion, what we are saying is this is motion of a body which is thrown in the air, which is just moving with some velocity, and it is under the influence of gravity. So, here we have neglected any other force which would be acting, which would act on the body other than gravity. Practically, when we look at motion of a light body in air, let us say a feather moving in air, then in addition to gravity, the air may exert force on the body, and such forces are referred to as drag and lift force on the body, and if these forces are acting, then the projectile motion will not be the type of motion which this body will show. And this is what we see when we observe the movement of a feather. It does not follow a parabolic path, and that is because these other forces are also significant and they cause some other acceleration on the body. Whereas the projectile motion which we have said, when we talk of it, we are assuming that gravity is the only force acting on the body. So, with this we have completed the projectile motion and discussion of kinematics of motion in a planar path. We will look at some examples in the next class, and after which we will come to dynamics, which is the forces that cause the motion. In kinematics, when we study, we only study motion. We do not study what causes the motion, and an important part of our study of mechanics will be how motion is caused, and that is what will follow in dynamics.